You're not doing it independently, you're kind of interacting a little bit. Anyway, so we are going to calculate the loss in elastic shortening, relaxation, creep, and shrinkage, because it's a pre-tension beam, and we are not even considering the anchorage seating loss, although there is some, we are not being asked to do that. So elastic shortening, so nothing is given. In the exam, I had given you all these bending moments for dead and live loads. So based on the value given for the geometry here, I calculated the weight by 30 by 50 is the outside dimension, 30 and 50. Subtract the two rectangles, which is one here and one here. Right? Those two subtracted from the overall, you can get 4.75 foot square, or you can do, three different elements, it doesn't matter. And so you get 4.75 times 150 pounds per cubic foot. So every linear foot, right, will have 730, so your bending moment is 713, which is in pounds. 75 is in feet, so you multiply all this result foot pound into inch pound by multiplying by 12. So this 12 is for that, right? And then 8 is of course the WL square over 8. So this is 6 million inch pound, and the live load according to the weight, the WL is given as 1200, so that live load is, bending moment is 10 million, right, roughly speaking. And you put, what my practice is to leave the commas there at every 3, like we do in US, from the right hand side 3, and goes on in series of 3s, to make sure you don't lose anything, right? That's just to make sure, because we are all human beings, and if you didn't put the commas, nothing is wrong, but you may mess it up, you will drop something. So it's better to have it, so that you will know that this number is 6 million, not 600,000, in case you miss something. So it's a good idea to leave the commas there. But anyway, FPI is given as 70% of FPU, so it's 189, right? Versus 202 in the exam, right? So PI is, we are checking elastic shortening, so I took the PI, FPI, and I subtracted what I'm doing below. In other words, the order is messed up, right? So you go down and you calculate the relaxation loss right here from at the time of transfer, so which is 18 hours, I believe, right? So here's what I did. Again, it doesn't tell you, sorry, I said 18 hours, but it doesn't tell you what is the time frame for relaxation. So rather than assuming something arbitrarily, 2 days or 3 days, which can be done, but to be logical about this, you can use this formula where FCI is equal to T divided by L plus beta T, assuming steam cure, which is more common for pre-tension members, right? So this is the formula to calculate the stress given the time. So we don't know the time, so we just flip the expression to get T equal to this, right? So at that time, which is 2.61 days or 63 hours, your strength will be 4,500 PCI, right? Or pounds per square inch, PSI, right? So if you have used 2 days or picked a number, it's okay for our purpose. But if you want to be somewhat more accurate, then you should do this way. Unless the problem tells you how many hours it is to the transfer, right? If it gives you only 4,500, then you put the 4,500, which is 6 versus this is the FC, and this 4.5 is the 4,500, right? So that's what I did. So FCI is 45 and FC is 6. That's what I have used, and back calculated the time. So anyway, so based on that, I can put my log 63 for log T, right? And so I get my 9,241 PSI. So this is my relaxation loss up to 63 hours, right? So I go back here because my elastic shortening is happening at 63 hours. At that point, my pre-stress is really 189 minus 9241 we just calculated, right? So that's what I have done here. So that's why I said, see page 3. And this is my area to give my pre-stress force, right? So I'm going to use force, and I'm going to calculate R square is not given, so IC, which is 1 over 12. Again, the same idea. This is the I of the big rectangle, and this is the 2 rectangles subtracted. They're all at the same center line, so you could do that, right? The neutral axis both. This is the vacuum or deduction, so you get 342. Or you can do the other way. There is a longer way of doing it, right? So I over A, which we already know 684. So the superimposed dead load is given as 30% of the live load. So it is 3 million. So this is not given, it's given indirectly as 30%. So that's your superimposed dead load. And now we can calculate the FCS or stress like we have done before, 1164. And then I calculate my N based on ECI of 5700 square root of 4500, which is 3.824 versus 27 for the strand, right? I dropped the 10 raised to power 6 because they both are in 10 raised to power 6, right? So the N is usually in the range of 6 to 10. So if you get 15, then something is wrong. If you get 2, something is wrong. So it should be in the range of 6 to 10, right? So I got 7 in this case. And so the elastic shortening is that, 8,200. So the net PI is 189 minus the relaxation and elastic shortening. So here's where it becomes interesting. So I get a stress of 171,541 PSI. So my PI is really 524, but I have used 550, right? So this was the argument I was giving you, that for elastic shortening, it is a sequential, you can use a couple of or 3 cycles to correct yourself, right? So I'm saying here that I could reduce my PI that I had calculated being 550,000 to 524,000, right? So it's about, how much is that difference? Anyway, slightly lower anyway. So when you use that, your value becomes 1088 PSI versus 1164, right? So I'm just becoming an accountant. I'm trying to be smart or more accurate, but it's not amount to a whole lot. But it just says that it does have some effect. But then I can say that, hey, now my loss is 7,600 versus my loss was 8,200. So few hundred PSI difference is not a huge deal, but it does make some difference, right? So then I make a note here that you may continue doing this cyclic motion a couple of more times, but we are not looking for that kind of accuracy, right? So relaxation loss, we talked about that, right? So now I go to stage 2, in this case is called and the transfer to 5 years. So from transfer to 5 years, the creep loss is very simple. You calculate the stress at the center of the strand, and you subtract that from the stress you just calculated above, right? This is the superimposed dead load stuff, right? So this is the superimposed dead load moment, and this is the stress for superimposed dead load that you have lost at the center of the strand. So you reduce that, and you get your creep loss as that. And similarly, shrinkage loss, no big deal. Your T1 is 63, and your T2 is this. And so I said, shrinkage loss is pretty straightforward. I'm sorry, I'm mixing up the numbers. But shrinkage loss is one number, basically. It is not time dependent. It is for ultimate value, for our case, right? There is another formula in the book that gives you shrinkage for a time also, right? If you are interested. But usually it's calculated for a long term. Call it what you may, right? So here is the relaxation from 63 hours to 43,800 hours, which is 5 years, right? So if you think like this, our life has a few 100,000 hours, we are not that, we don't live that long, right? So if you can calculate for 80 years, how much is the life? Anyway, long story short, your relaxation loss from 63 hours, so this is 9,600 psi, just like the other example or your test. So if you add up all this stage 1 and 2, you get 41,000, and compared to 45,000 given as a lump sum by ASHTO. So you are comparing that, which is what is required, right? Okay, so that's what we had for assignment, although I have begun doing it, but I really didn't finish. So I thought I'll discuss this, get it behind us, and I'll bring you the graded assignment next time. Okay, so what else do we want to talk? To complete chapter 3, we need to do 2 more things. One is we didn't have any example for the seating loss and for the friction loss. So we'll do that, and then we'll do a long assignment. So let's see if we can finish all that. A long example at the end of chapter 3. So let's see. This one. This is the example we have been carrying on so far for the other losses. Sorry, this is not the right one. This one is what we meant. Okay, this is series of the same example as example 3.1 that we have been using in the class. It's in your textbook. What we haven't done in this case is the bottom 2 portions where we talk about the friction loss. We haven't done this, so let's look at how you actually do it. So in this case, assume example 3.2 has tendon profile as shown. The tendon made of 7-wire uncoated strand. Now, why are we talking uncoated? Because we are talking about friction. So we need to know what kind of strand this is, coated or uncoated. In what kind of seating, is it flexible or stiff? So we are talking about what kind of material we have for the seating or for the duct. Compute frictional loss of stresses in pre-stressing wires due to curvature and wobble effect. So curvature effect is something you can calculate in a design office. The wobble effect has to do with the one where you have imperfections or the lack of skill in laying things out, right? Or accidental dimple in your duct or whatever imperfections you have, right? So we're going to calculate all that. So PI is 309,825 from before. FPI is 202,500, which is what we calculated, 70. I think it was 75% of the 270, right? So that's 202,500. This is what you had in your test also, right? So these will repeat because this is standard procedure, right? Not that always repeat, but it will repeat. So now, like I said, the angle alpha is nothing different than 8y over x. So your eccentricity, at support is 0, and at midspan is 11 inches, given, right? So your y is really 11, and 8 times 11 is 88, divided by the length, which is 50 is the span, multiplied by 12 to get the same units, right? So make sure your units, everything is in inches. Otherwise, you will get this very bad. You will get this very high and you will have a problem. You don't have any loss then, right? So you want to use 0.147 as your alpha, or you will have a huge loss rather. Never mind. If you didn't multiply by 12 in the denominator, you'll get a big loss. Again, if you check yourself, and if you get a huge difference from 45,000 as being the lump sum value given by the ASHTO organization, then you should go back and see what you have done wrong. So anyway, so I'm calculating the friction loss as 18,000 based on the curvature and wobble. So how did I get these values? This 0.2 is from table 3.7 and 0.00125 is in table 3.7 also. So let's look at that table 3.7. Here. Somewhere here I have a copy of the table, I think. So if I go to the textbook, where is my textbook stuff? Here, text pages, chapter 3. I think I have that table. And where's my quotation? This is the table I'm referring to for the pre-tensioning strand 45,000, right? So always keep that in mind if you get much beyond that. Here's your table 3.7, right? So it says the type of tendon, the wobble coefficient K, and the curvature coefficient mu. This is the friction part, the second one. And the first one is the skill part. K is for how skillfully, how nicely, how perfectly you have done the job in the field, laying out your duct, and how much lack of imperfection do you have. More imperfection, more. So it is kind of a estimate, really. Curvature is more accurate because it is a profile you know. So anyway, and there are a lot of range here, right? There's a lot of range here and different values here. So let's see, for example, tendon in flexible metal seating. Your values for the wobble effect is 1,000 to 1,500, or sorry, 10,000 rather. 001? 1,000, never mind. 001 is 1,000 of, so it's like 0.1%, right? And versus 1.5 or 50% more for a wire tendon. For 7-wire strand is 305 to 202. And if you look at the tendon in rigid metal duct, these values versus those very inflexible is one number, and this is 302 versus 201 and 2015. So there's an order of magnitude difference could be there, is what I'm saying. Because this is a rigid, so it is a lower value compared to these numbers. Not always, but depending on how good a, what kind of bar you have. For example, for bar, the values are lower because the bar doesn't have much curvature anyway, right? Your strand will have more. So the bar is different than 7-wire strands and then wire. And flexible sealing has generally more value than the rigid duct, okay? Because the flexible one can collapse more easily and more defects. So wobble effects are more in flexible material, is what the whole thing is. And then these mastic coated versus pre-greased, these are the values. Now the curvature effect is 0.15 to 0.25 here, and for metal duct also 0.15 to 0.25. So it doesn't matter in this case because your profile is what determines this, not the flexibility, right? Depending on what profile you have. And then if you're lubricated or you have a coated surface, then your values go down, right? These are the values at the bottom. These two are less than those values, is what I'm trying to point out, right? Because you have a better material that are coated or lubricated. So friction is less, so friction loss is less, right? So this all makes sense. So these values, now there is a range. What I have done is I've taken the average. Now book has taken, I believe, the extreme values. Like it has taken 0.2, where let's see, the mu right here is, well, it has taken average anyway, never mind. And then here it has taken the extreme for the wobble effect. Wobble effect for 7-wire strand in a flexible seating is what we have, right? We have flexible seating and 7-wire strand, and the book has this value, right? 0.002, which is what you have here, 002. What I think we should do, unless you know that the people are really poorly skilled, you should use average value, right? That's why I was coming. My suggestion. Huh?
That's where that question is coming.
So you have to know your crew, in other words, what kind of people are doing this job, right? So depending on how much you know, it's subjective, in other words, right? So book has been conservative, and there's nothing wrong with it, as long as you explain and understand what you're doing, right? Okay. So if I go back to my calculations then, that I was doing, oops, where are we? Thought I had it here. So let's see. Handling example, chapter 3, set 1. I can open only one at a time, seems like. There must be a way to open two. Okay. So let's see where we are, right here. And we are calculating friction. So I have taken average value here, and I've taken also average value. Your book has average in one case and extreme in the other, right? So you can explain, you can assume, or you can explain that I'm using average value, or I'm using average here, and I'm using conservatively high, depending on what you want to decide. So there is some leeway, if you will, or your judgment, right? So anyway, I got 18,000. I don't know what book was, probably more anyway. So the next example is very simple, like I said. This has to do with the compute the anchorage seating loss for in the post-tension beam of example 3.2 with estimated slip of 1/4 of an inch as given by the manufacturer. So as you seat your wedges onto the wire or your stand, you're going to lose 1/4 of an inch, right? You follow me? Anybody has question on how we lose? Okay. Why is it only on one side? Why not double this? Because you have wedges on both sides, probably. But the opposite end, when you're pulling from one side, the other side is already gripped if you're pulling, right? There's no loss on the other side. Unless you have 2 jacks or something, then you have to have a double. You need to know your process, in other words, right? If you simply have wedges already put in and hammered into place, and you're pulling only on one side, you can do that, right? The other side already gripped by force. You just tap it into place and then you pull. So now you have pulled your force, now you let go, the other side is already gripped, right? So this is only on one side. If you know for a fact that you have 2 jacks on both sides, which is given to you, then you should double this amount, because you will lose both sides, right? Anyway, so this, your 1/4 inch divided by the entire length, which is 600 inches, is a very small number, but then because of the EPS being this high, it becomes 11,000 PSI. You see, it may seem like 1/4 of an inch, but you lost a lot. 10,000, 11,000 is not a small amount, but it does happen, right? Okay. All right, so let's see, what else are we having here? We are going to do the example in the book, and we'll do what we can in the class, and then you guys can read the rest of the way. Let's see how much, because next time we will start chapter 4. We already kind of started, but that's how we will start. Okay, so the, this right here, actually, I'm going to get to chapter 3. Okay. So this is the example at the end of chapter 3. A simply supported pretension. What we are going through in this is we have 3 stages, A, B, C. Stage 1 is at transfer. Stage 2 is after concrete topping is placed. And stage 3 is 2 years. You're losing, this is like a depreciation of your machinery. If you know in engineering economics, you must have studied this. Those of you who have done any other economics class, you know depreciation is a continuous process, right? So we are sort of doing that. As time goes by, we are losing more and more, right? But we are asymptotically reaching, just like depreciation, after 15 years, it's all old now. You know, you lost all pretty much. Depending on your material, like if you have electronics, it's like 3 years. The IRS gives you a certain time, you know, if you have tax deduction and all that. Tax time right now, so I know it for a fact. Anyway, so ours is like a depreciation. It goes on and on, right? So we are checking all this loss at transfer at when the topping is placed, and the last one is 2 years. So a simply supported pretension 70-foot span, etc., is pre-stressed using 12 half-inch diameter 270 grade stress relieved strands, right? So stress relieved means our formula is for stress relieved, for relaxation. The strands are harped, and E is 18.73 at the mid-span and 12.98 at ends. I've been walking a lot, so I'm relaxing my feet, so I hope you don't mind. So in other words, we have not 0 eccentricity. We have 12 inches here and 18 or 17 inches here, so there is difference of about 6 or 7 inches here between them, so it's not as big a difference, right? That's the whole point. Why are we looking at this? Because our Y now is not going to be 18. It's the difference between 18 and 12 probably, right? Okay, compute the pre-stress losses at critical section in the beam. Yeah, I forgot this one. due to dead load and SDL, assume critical section be 0.4 L. Sometimes your critical section, depending on moving loads and all that, may not be at mid-span. It may be slightly off, or your load may be not uniform. You have a load that's skewed more on left side and not on the right side. So your critical section may be at 0.4 in place of 0.5, which is the mid-span, right? It depends on the load distribution, right? So your critical section could be 0.4 L of the span, considering that it can sometimes govern the case of moving loads also in continuous spans. So continuous span maximum load may not be mid-span, depending on the profile of your, so you may have a continuous beam that may have uneven, this is L1, this is L2 and L3, and if I'm looking at this may not be mid-span, because you have load here, here, and here, so it may be here, not exactly in the middle. You have to look at the bending moment diagram, right? Find out where the critical maximum moment is, right? Depending on, if L1, L2, and L3 are same, then probably, and the load is uniform, then it is still mid-span, but it may not be. Load may be uneven, the span may be uneven, whatever, right?
Alright.
So you're going to put this monkey wrench, if you will, of 0.4 L, so now your life is a little bit more complicated. So suppose topping is 2 inches, now this is all given to you. Suppose the topping is 2-inch normal weight concrete. Is this pretension lightweight concrete? So your member is lightweight, but the topping is regular weight, just to give you a different flavor. And steam cured. And double T section, double T has two stems coming down on a slab, right? So double T. Okay, so suppose also the prestressed transfer occurs at 18 hours after tensioning of the strands, and given FC is 5,000 and FCI is 3,500, right? Now you can check out if 18 hours will do this or not, but this is already given to you. 18 hours may not give you 3,500, but you are told to do that, right? Otherwise, we have that formula for steam cured, like I showed you, right? If 18 hours is not given. Or if 3,500 is not given, then you can calculate your strength at 18 hours, right? Either way. Anyway, and these are your cross-section values. AC is 615, IC is 59,000. CBE and CT, what is that?
Central.
The distance to the extreme fiber from neutral axis is not equal, right? Obviously, because our section is double T, right? It has a T and has a double T like that. So the neutral axis is somewhere here. So this is shorter. This is CB and this is CT, right? So this is smaller than that. CT is 10 and CB is 21, right? All together is 22, right? So this whole thing is 22. So this is 10, this is whatever, right? And then your WD is 491 PLF. You can calculate if you have the patience by the size and all that. And the WSD 2-inch topping is already given to you, right? If it is not, you can always calculate based on what this width is, that they will cover this with the topping. So what is topping means? That you have this precast member from factory, and then you put this as a wearing surface on the top, right? So that you put another one here, you don't have a joint open that will leak on you, for example, right? So there are ways to do that. This is one of the ways. And WL is 40 PSF, transient. So hey, it's very clear the live load is transient, right? It's not sustained, right? That's the way it should be. It should be very clarified. FPU is 270, FPY is 85%, is 230. It's given to you. And FPI is 70%, which is 189, and FPS or EPS is 28. That varies slightly. Sometimes it's 27, sometimes 28 or 29 even, depending on the type of material, how you braided it, it will be different. Okay, so it's given. So here's the cross-section view. This is the topping on top, and that's the 2 inches. And this is all is given actually, right? So you can actually calculate some of this if you're interested, but it's all given to you. Sometimes you'll be asked to do that, And then there are catalogs by PCI, Prestressed Concrete Institute, will have sections, standard sections like these that we will discuss in chapter 4. So you can pick your section from catalog, which will work for you or not, depending on how much section more or less demand is and all that, right? Okay, so solution. So we have, our case is pre-tension beam, right? So remember that. So we don't have the friction loss, for example, right? So we are supposed to calculate stage 1. They don't tell you which one to calculate. You have to figure out. So make sure you don't do anything. So here it is, pre-stress losses, relaxation from 0 to 18 hours, right? So this is the first one in the right order. Remember in the other one, I did the elastic shortening first, then I realized, oh, I need to go back and fix it. But this is the right way of doing it. You should do the relaxation. So by the time 18 hours comes, you know how much you have already lost, right? So you're going by hour to hour, in other words, in short term. So in 18 hours, you lost 6,400 PSI. Now your pre-stress for elastic shortening is already reduced to 182 versus 189 that you started out with, right? So you're keeping a track on your what pre-stress is as things go by, right? So here's in 182, and then your elastic shortening, depending on ES over EC, which is 11.62 here because of the EC value at 18 hours, right? Is 615 is the area, PI is 335, all that R square is calculated here, I over A, not given to you, so you calculate. E at, oh, here's the interesting part, the eccentricity at 0.4 L is really this. 18 is at the center line or in mid-span, and 12.98 is at the end of the span, right? So that's the difference. Well, that will be the difference at 0.5, so 0.4 you should normalize it for, you know, that for 80% of that, plus 12.98. So all that is 17.58. And R square is I over A, and MD is, again, not very straightforward, right? To give you a different, this is in the, how many of you have done steel design? Okay, so you have the AISC book there, formula, and I'll give you, because some of you haven't done steel or don't have AISC book. So formula like this will be needed. You should know this formula, but if you don't, that's okay. WL square over 8 should be known. If you don't, then you are, go back to undergraduate, right? Okay, so WX over 2L minus X will give you this value at 0.4. Now we are using L, let me see now, what are we doing? 28 is your, what is 28? What's the span?
Distance from
0.4L,
yeah,
right?
Yes.
0.4 times 70.
Yeah.
And then L minus X is 42, which is 70 minus 28, right? So this is 42. And this is the conversion factor from inch to feet of 12. So you get 3 million. If you don't put 12, you will not get million, you will get hundreds of thousands, then you get suspicious, because in this unit, inch and pound, you should be in millions for bending moment, typically speaking, right? For normal beams. So make sure you don't forget this 12. IC is 59.
Oh, where does the X come from? What is that X?
Okay, so if you have a beam like this, and you have a uniform load, and if I want to know my bending moment at X, not at midspan, it's WL squared over 8. Here it is that at X distance. This is L.
Oh.
So you have to use that formula for my bending moment at this location, right? So
the 20X is given.
X is given as 0.4 L in the problem.
Oh.
That this is our critical section because of, we don't know what it is, right? We're not even told, but if you look at your
assumption.
Depending on, yeah, because different spans, or your load is not uniform, or whatever, right? Or moving load, so many things. Okay, so we are not here into analysis of structures, so that's why you just take it for given basically is what it needs, right?
Mm.
And many times it is not, so that's the reason. So anyway, substituting all these values that were not provided, that we have calculated, your FCS is 1259, that we have calculated a couple of times now, right? So you calculate that, multiply that by the N, which is 11.62, you get 14,000 PSI. So now you're subtracting from 189, this plus this, you get 167,000. So your F6CS is 167 divided by 182 to get it a little more accurate, right? In fact, in this case, what I have done is I want to show you that eventually it kind of calms down. In other words, you after 2 or 3 cycles of this substitution, like FCS is calculated, you calculate the loss, then because of the loss, you have to change your values because you used 182 here, right? What was that? Your stress was 182 somewhere. Yeah, this 182 is what we started out with, right? So I'm going to say because we used FPI 182, but really if you subtract all this, you get your, after this loss we just calculated, it should be 167. Because we are talking about elastic shortening, right? The load applied will depend on elastic shortening, which in turn depends on the load and so on and so forth, right? So we are going into cycles basically. We are chasing our tail, if you will, right? So if you're doing this, then you get a slightly different number, 12,500. So when I do 12,500, I get a slightly different PI, and then I get, so eventually what happens is the PI becomes practically same. This PI, the applied force, or stress, it should be FPI, never mind. The pre-stress force that you had assumed 170 in the last cycle, it becomes 169. Now I'm saying that this is not even 1%, so let's forget it, right? So somewhere you have to say that's good enough for me. It's really not even, it's a fraction of a percent really, right? So you stop there. What I'm trying to say is the loss, which is, final loss is 12,000. What was the initial loss in the first step? What was the first step right here? 14,600. So we a difference of 2,000. So what's the ratio of 2,000 versus 14,000? 2 over 14, 1/7. It's about 10-15% of one item, elastic shortening. Overall, it is, if you talk about the overall loss, 2,000 versus 40,000 is not worth the effort, but it just tells you why is it trivial to do this, to go this much, right? You may go second step, but not this many, all right? You're trying to calculate something that you know is approximate anyway, right? So if it depends on how patient you are and how much being asked. If somebody in your test, or if your boss, or if you're doing something very critical, then maybe you do, right? Or in case of the classroom, if I say, calculate the elastic shortening accurately, and you do this, right? If I'm very emphatic about that, right? Okay, so this is the accurate number because now we have stabilized at roughly 170,000, right? Where was that now? Right there, 169.7 versus 170. The difference is so small between the two last steps, right? So anyway, no need to repeat. The creep loss is 0. Is that making sense? Because our stage is the 18 hours. No creep loss. No shrinkage loss because nothing practically has happened, right? No loss because the concrete might be shrinking for 18 hours, but it doesn't affect us in terms of loss. So at that stage, we have lost 19,000 PSI for 18 hours. Relaxation, elastic shortening, blah, 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 all those things, right? We have 3 or 4 items here. Well, the last 2 are 0, right? The creep and shrinkage. So we have only elastic shortening and relaxation for 18 hours. That's a big chunk, really. It's about half the loss anyway, right? Okay, at the end of the stage, FPI is 189 minus 19,000, so 169 is our pre-stress at 18 hours, right? So next time it should not go up unless you are talking about the last step, then it goes up, right? But anyway, stage 2 is transfer to addition of 2-inch concrete, so 18 hours to 2-inch concrete topping at 30 days. So we are going from 18 hours or 1.5 day, not 3/4 of a day rather, to 30 days. That's our delta, if you will, right? So we are going to, so the ES is given, EC now is 2.88 10⁻⁶. Where is that, page 2? Where is my EC? 2.41 10⁻⁶. That's my EC at, ECI, let me see now. Okay, I didn't explain this to you, but EC depends on, why are we using this formula, not the 57,000? Because this is lightweight concrete, right? That 57,000 works for normal weight concrete, normal stone aggregate. If you use lightweight aggregate, then use this formula.
What do you mean by lightweight, by the way?
See, this 115 pound is the weight per cubic foot of lightweight versus 150 pounds.
Wait, excuse me. When you talk about lightweight, you're talking about mortar, in this case?
We're talking about the aggregate is lightweight.
Lightweight is the one with the aggregate.
Yeah, that's the only thing you can control, right? Your cement is not going to be any different, water is not going to be different, sand maybe. Your aggregate is lighter weight. The type of stone you use, sometimes artificial stone, artificial material to make it light. Your structure is light, your foundation is light. You do sometimes.
Right.
That's light means not this light, it's the weight is light.
Which one is better? Normal weight and the lightweight?
Lightweight, you have to pay more, but if you're in a sensitive area where your foundation has to be light,
Oh, okay.
so then, or your columns have to be light or something, sometimes you do that. So lightweight is used with spatial aggregates. Anyway, so this is the formula, this 115, if you put 150 here, then you'll be back to the same formula, you'll get the same results. Right, so we are using 115 to the power 1.5, 33, and this is your strength at that point. And so at 28 days, it is 5,000. At 18 hours, it's 3,500. So your EC at 18 hours is 2.4 versus 2.88 at 28 days. Right? So let's go back to here at stage 2. From 18 hours to 30 days, we are going to use the elastic modulus of 18 hours because that's where our stage is beginning. Right? You could arguably put something different, but this is all we got. You can argue that why don't we use the average between 18 hours and 30 days, right? You can argue like this, but we are not in that business. It's your choice. You can explain away that this is what I want to do. Right? As long as you explain, right? Because, like I said, these are not very accurate, not as accurate as you would like to be, right? It should be something between 18 hours and 30 days, just to complete the argument, right? But for simplicity, we are using 18 days. All right, so 18 days EC is 9.72. Okay. And then FCS is 1103 that we have calculated before, and W topping is 250 pounds because it is regular weight. It is 150 PSF, this right here, right? Oops. It's 150 pounds. So MSD due to topping is this. Again, our formula is not WL square over 8, it is that crooked formula, right? So you put all that, you get 1.7 million inch pound. And so FSD, because of superimposed dead load, is MSD E over I, which is the E is 17.58 we had calculated at 0.4, right? And then I is 59,000 that we had calculated up on top. So you get 519 PSI, and so relaxation loss, sorry, this is FSSD now. We will use this down below. But relaxation loss, we are using the same formula, 720 hours for 30 days and 18 hours subtracted in logarithmic difference. and divided by 10 because we don't have load relaxation specification. Stress relief is what we have, I think. Let's see, what do we have here? Stress relief, right? It's not load relaxation, so our formula is 10. So you're going down here. There. So we are 10, so 5,000 PSI loss in relaxation between 18 hours versus 30 days. Creep loss. Now, creep loss is calculated here forever, basically, as a lump sum. And so is the shrinkage loss, right? Now, you may argue about this, and you may select to use the other formula, which is time dependent. There is another formula as an alternative that has to do with logarithmic of time, and there is a factor and all that, right? Alternatively. So you could do that, but that's your choice. Then you can calculate in the third stage and subtract this much from there and all that, right? This is the ultimate value. This is the value in a very long term, independent of time. And then the shrinkage is also same way. No difference between what we are doing here, and the only thing we did is the FCSD we calculated here. What was that? Right there. 519 is being utilized here, 519 for your creep, right?
A question. Why we use this FCS the same as the beginning?
This one?
Yes.
This one should be the one we have before the superimposed load. That's the stress.
But due to the step, the shrinkage loss and elastic loss is already there.
For the
For the
18 hours?
yes.
And you could be right. This may not be as accurate as you would like to claim. What was the stress? Let's see.
The relaxation loss and elastic.
What was did we calculate the stress? Here we are. 1070, is that what you're pointing out? 1076? 1103 was the last one, very last one. See this? I'm keeping track. So this is the last, most accurate number we calculated, right? Based on the losses up to that point.
No, I mean after the relaxation loss.
Mm-hmm. This is before. This is the stress
Before the relaxation.
before the superimposed dead load was applied.
Oh.
You have losses from relaxation up to 18 hours. You have losses because of elastic shortening.
Oh.
Those are subtracted, and the elastic shortening was the one where we do it 2 or 3 times for accuracy. You know, we were getting different numbers, right? 1076, 1103, and 1259. All those are valid numbers, but we use the most accurate one because we happen to have calculated. Otherwise, there's nothing wrong. You can stop at 1259 and say, hey, that's accurate enough for me, right?
Okay.
You with me? Okay. And I could have used 1259. I don't know what your book has done. I can't remember now. It might have used. I don't think it went through all these cycles. Okay. So if I go back here, so I'm going slowly here so that we don't miss anything. So 1103 minus 519 we just calculated, so you got 9,000 PSI as your creep loss for long term. Although we call it 30 days, but it really is for the long term, right? This is not for 30 days. You can do some manipulation to find out what it is at 30 days, right? And this one is same way, but I think there is a formula for time-dependent formula on shrinkage also, right? You could use that. Okay. But this is the final value in the long term. So the sum of loss at stage 2, see, this is not accurate, right? So all this added to 20,000, and then increase in pre-stress due to overlay weight. Remember that? So this is increase now, because we put the overlay, we put the superimposed dead load now. Not the live load, just superimposed dead load. So you added about 5,000 PSI by N time FSCSD. The same 519 times 9.72, which is the module ratio, right? So you're adding, this is the one addition that you don't want to forget. You with me, everybody? Okay. All right. So here's what we did. FPE is pre-stress that we have calculated, and plus this. This is the loss, this is the gain, right? So you add, you subtracted the 20,000 we just calculated here. What was that? Right, that's 20,369, 20,369 plus this 5,048. So you are at 154,000 PSI. Remember we started 189, right? 189 was the stress at the beginning. So we are down to 154. So we are keeping track, in other words, right? And in your design, at this stage, you will be calculating your top fiber stress, bottom fiber stress, and all that, right? If you are selecting a section, you need to check what kind of stresses are you getting. We are not doing that. We are simply blindly going and just keeping track of the pre-stress losses. That's all we are doing, right? But in the design, this number should be used with these moments we have considered for the stresses, right? Okay. Stage 3, so end of 2 years. Relaxation loss is still continuing, right? Because we have a formula that's time dependent, and we found out 2,500 more using the same formula, 2 years is 17,000 hours, and the 30 days is 720 hours, so that's subtracted. The rest is all the same, except this keeps dropping down for you, right, every time. So the last one we calculated is put here, right? Otherwise, it's the same formula, right? And then 0.55 is still the same. So this is a small number, but that's what it is. So the other shrinkage and creep is already calculated, so the loss is another 2,500 from that 154. So you get 151,000, right? So you divide this by the original, you get 20% loss. 80%, this is 80% of this, so your loss is about 20%, right? What is the loss? 189 minus 151 is 38,000 roughly, not quite 40. But we are calculating at 2 years, right? So there is a slight decrease because of that. Right? That's the only reason. Otherwise, it should be around 40 or so. Okay. So solve the same problem, assuming the beam is post-tension, right? So the same double T section, same all these properties and everything, but you assume that you will be post-tensioning this as opposed to pre-tension. So we have to consider the other kinds of losses that we haven't considered in case of pre-tensioning, which is the anchorage and friction, right? So these two will be considered from the jacking force, right? So, all right, post-tension by simultaneous jacking. Why is it important? Elastic shortening is 0. Right? Right. So that's the key. Elastic shortening of all strands in a flexible duct. Why flexible duct? That will tell you how much friction you will lose, right? So that's why you're providing all these clues. It's like an algebra problem. You give them some clues so that you can solve the problem, right? Or you will have to assume. If nobody gives you what kind of duct, then you have to say, assume this is the duct, right? That you like. Or if you don't tell you how this jacking is done, then you assume that you will be doing it one at a time or something, right? So this is given to you, so you follow otherwise you will have to assume. Assume total jacking force before any pre-stress loss. It results in jacking force of 189. Or you find your own 0.7 times the FPU or 0.75 times FPU. You can always, because the code tells you what should be the jacking force, right? It should not be more than 75%, so this is 70% in this case, right? Okay. Why is it 70, not 70? Why wouldn't you go more? 75 is allowed, right? Why would you not go? Because you found out that you don't have as much load on your beam. This is the beam you have selected. 70% is good enough after all the losses, right? That's behind the scene. If you were to be a design engineer, you will be selecting this number, right? Or you will be selecting, in other words, how many strands you're putting. Either way, you will be doing some decision making, right? So anyway, In other words, you do this and you find out you're failing somewhere, your stresses are too high, then you say, no, I need to back it down a little bit. Or I need to increase some more because my stresses are too low, right? So that decision has to be done by trial and error. You have to do it sequentially. Anyway, so let's see, the anchorage loss is very simple, quarter inch divided by the length multiplied by the E. So that's your anchorage seating loss, right? Right. Was it given? Yeah, it says here quarter inch, right? Okay, so that's that. The friction loss is F1 is 189, which is the jacking force. That's the force you have applied, right? And then mu alpha. So I've used mu of 0.2 as the average value on table 3.7 for flexible duct. And then I've calculated alpha being the equation 323 of 8y over x. Now remember this, y is the difference between the two, right? 18 versus 12.98. This is what we calculated at 0.4 L, right? And this is at the end. So the difference between the two is the delta y, right? Because right? You with me? Pratik? This clear? Okay. So y is the difference between the two, not the midspan, but at 0.4 L, right? And then so this is the length, and this is your radius. Who was asking radians? So that's radian. The ratio between the two is radian, right? So that's a radian. So this K is based on the flexible duct is 0.00125 average value of the two values given for flexible duct. And you plug that in, and you get 18,000 psi as your friction loss. That's a big loss, isn't it? Okay, so at that stage, you have lost 18,000 here and 8,000 there, right? Friction and what was the other one? Seating loss, right? Seating loss and friction loss has happened. Okay. So at this point, the losses are relaxation and creep and shrinkage. So we need to calculate all those, right? ES or elastic shortening is 0, like I said, right? So we need to calculate these. So transfer at 18 hours of pre-tensioning. The relaxation is very simple formula, right? We know all this. 18 here for log T, and this is stress relief, so 10, not the low relaxation. And 162 FPI. Why is that? Why not 189 here? This is the problem. We are post-tensioned, so we have a loss right away, right? The friction and the other one, the seating. So 162. The relaxation will start at this stress because you lost more than the pre-tensioning case, right? So we get this lower value. If it was pre-tension, we will use a higher value on the numerator here, right? Okay. So it is 3,000 psi, and creep and shrinkage is especially because of post-tensioning, creep and shrinkage doesn't matter at this. Even if you have the shrinkage is happening, but it doesn't affect us. And creep won't start because you haven't applied any load at 18 hours. Because that's when you start. At 18 hours is when you transfer the load, right? Usually in post-tensioning, you wait a little longer though. But that's what they want to. You want to solve the same problem on same stages for post-tensioning. That's why we are considering 18 hours. Otherwise, it will be many days or weeks, right? So in any case, so your delta FT at this stage 1 is 30,000. These are before, and this is the one we just calculated, the relaxation. And these two are practically 0. Or 0 really, in this case. Stage 1 we are at 158. At the end, at the stage 1 when we are transferring, the pre-stress is 158 versus 189, right? 30,000 PSI lost already. 30-day topping placement, you're calculating all the values, or given anyway, because these were all on page 4 that we have done for pre-tensioning, so we are using the same numbers, right? The weight, the N, and then the moment at 0.4 L. Remember 0.4 L? So that's what that is. So the relaxation continues, no difference, right? It doesn't know post-tensioning or pre-tensioning. So this is, the only thing is, this number is different, right? Compared to pre-tensioning. So this number may not be exactly the same. I don't know what it was because of this difference. Because we have lost a whole lot more now, right? You with me? Okay. So it is 3,500 for this. Creep loss. What's going to be different here? The stresses, these numbers may not be exactly same. So FCS is 964. We had 1,000 or 1,100 here, right? So slight differences because of the way the losses are different, right? Bigger loss in the beginning. So this is smaller because the applied stress is less, so the creep is less, right? Applied stress is less, creep is less. Make sense? Because we lost things very quickly. So the creep loss is 5,500, I hope. This is, how does it compare with the previous one? I didn't make the comparison. So this creep loss at stage 2 is 5,500, and in this one at stage 2, creep loss is 9,000, right? So it is changing even though the formula is still the same, right? Because stresses are less. Right? Okay. So where are we? Oh, somewhere here, right? 3,500. Okay, and the creep loss is 5,500. Shrinkage loss, 3,590. Same as pre-tensioning. I didn't even bother, right? Because there is nothing to do with stress, right? The shortening will be same, so the loss is same. Okay. Oh, except KSH is 0.58 table. Let's look at table 3.8. I lied to you, I said something. Let's see. There are complexities, you know. In regular reinforced concrete, you don't have to do all this laborious work, but this is the problem. But you're mass producing, so it's okay. You do one time and you make thousands of these, right? So anyway, back on. Hopefully you do my mass production. Not for post-tensioning, but where we were, the textbook. So, table number 3.8. 3.7. Remember 3.8. What am I talking? I don't remember. I might have to explain next time. Let's see. 3.8.
You said table 3.8.
This is what I said here. I don't think there is such a thing exist anywhere. I don't know where I got this. I have to get back to you guys next time. All right? Okay, so we'll continue from here next time because I can't remember. There was something here. I'll get back to you. So we practically have finished this. In fact, we can do while we have a few minutes. Let's do one thing.
Is that the summary of stress?
Let's see here, hang on. I need to explain that later.
Okay.
So let's close this one. Where we are, right? This one. Oh, there. So, have opened so many here. I thought I don't. Let's close all this. Okay, so losses stage 2. Okay. Relaxation where we were anyway. So this is the last example, and we will get back to the end of example 3.9 next time. But example 310 is solve the problem of 3.8 and 9 by approximate lump sum method. So the lump sum method says that your loss is 45,000. So the stresses at the end of by lump sum method is 144,000 versus we have calculated 151,000 here, seems like, right there. Where is 158? There. 149, 148. I have used the wrong number. It should have been 148. So difference, the point is, the difference is 5%, and for post-tensioning it is 3% difference from the standard numbers. So in other words, you are not that far whether you do post-tension or pre-tension. 3% difference from what they give you, which is 148 in one case versus 154. If you take out 45,000 from the initial value versus 144 for post-tensioning, the difference between the two numbers is 3% for post-tensioning and 5% for pre-tensioning. So what we are saying is, it's an academic discussion sometimes, but sometimes you may not be doing a whole lot of benefit by going through all this motion, but you should know where it's coming from. You should know where it is coming from, so that you don't select the wrong material and have a better handle on this. Right? But it's not that big a deal. For preliminary calculation, when you're starting out something, to select the section, for example, you could use this rule of thumbs and then check it later, right, to see if it is really happening. Okay, so let me finish this next time. I'll look through that one little glitch I have, and then we'll continue on chapter 4. Right, I don't have any assignment picked, so you guys are okay. Next time we will have assignment, and then 2-3 weeks from now we will have a test. Right, so I'm just giving you a pre-warning actually, not next week for sure, but I'll let you know next time.
Can we have the PowerPoint and this example
Yes,
through your email?
I should have done first, but like I said, I woke up at 4:30 in the morning to go to Parkersburg to a chemical plant at 5 o'clock to reach there for safety training. You need to be safe, you don't want to kill yourself. So they tell you what not to do and all that. So I had to be there at 7:30. And then after the training, you walk around whole day. And I was determined to come to the class, so I came. Brought some drink with me.
Parkersburg is 3 hours drive from
2 hour plus, yeah. But that's okay, that's part of life. Barry will tell you, it's part of life. If you're doing a job, you need to be prepared. Yeah. This is unwinding part of the day, basically. It's good to see you, young fellows, learning all this, and I hope so far so good. If there is any question where you are really don't understand why we are doing it, please let's discuss that. Okay, I'm trying to preempt that by explaining, but I may not be doing all you want. So please ask questions like Robert asks many times. Not that he's the only one, but he's more than others. She asks also. But I want all you to open-minded and ask questions and study the book. Make sure you understand, because really I tell you what, the grades and all this will stay behind you. The long term, you really need to know what the heck you're talking, right? You may be happy with your grades for now, but really what sticks with you is how much you really understood and retain, and that's your long-term benefit, really. And I tell you what, even if you get A grade in throughout or most of the time, that doesn't show you're competent necessarily. So keep that in mind. What have you really retained, and how much you have really internalized, that you really can recall, and in the longer term is what matters. That's true education. That's my lecture for today, so I appreciate it. See you next time.